So I'm switching on the YouTube live stream.
Good, let's start then.
Meanwhile. Okay, so may I announce your talk?
Yes.
Okay, so I'm very glad to welcome Raf Cluckers from Lille and announce his talk on a partial overview of motivic and uniform p-adic integration.
Thank you for the invitation. So there is a hybrid setup with a live public and a virtual public, my first for that. So where does motivic and for that matter uniform p-adic integration sit inside the culture of mathematics? For me, this is centered around the very old questions and problems related to counting. And since a very long cultural history of humankind, one wants to bring in, or one brings in geometry and analysis just to study finite counting, finite sums. And in this tradition for millennia old, for me, motivic and uniform p-adic integration is where you can see it. But in the beginning, I will not talk about uniform p-adic or motivic integration. I fixed just for simplicity a field of p-adic numbers QP. And that's for the definitions and results become very concrete and very efficient to introduce in that simplicity. So a key object in this concrete setting of a fixed field of p-adic numbers is a definable set X subset of some Cartesian power of the p-adics. And I will give that definition here very concretely. It's some subset that you can obtain by finitely many iterations of some nice procedures. Namely, you take a polynomial in a tuple of variables X, you equate it to 0, and you do Boolean combinations and projections. Finite Boolean combinations and projections. And everything that you can obtain with a finite iteration of taking 0 loci of a polynomial, say, over the integers and projections, I call that a definable set. This is also sometimes called a semi-algebraic set. Another way of saying it is that I specify I'm talking about definable sets in the language of rings. And so in the language with a plus sign, a minus sign, times, and 0 and a 1 symbol. So definable in the language of rings is synonymous. But in this case of p-adic definable sets, there is a key simplification result for the definable sets. The simplification result here is sometimes also called an elimination of quantifiers, meaning you don't need the projections anymore in order to describe your sets. So it's quantifier elimination, and every definable set can be described by a simple Boolean combination, not involving any iteration of projections and Boolean combinations any longer, if you generalize a little bit the conditions you allow to talk about. Before I put polynomial equals 0, now I allow the condition saying polynomial being an nth power. So this is a symbol speaking of the non-zero nth powers inside QP. If you want a special case of that, for simplicity, you can also allow for some other polynomial conditions like being 0 or non-zero, but it can all be coded with the n powers. So this is a simplification. Of course, being an nth power or not was already a definable set, but just allowing this extra relation in the description of sets allows us to avoid the projections. Think of the real analogy where you have the ring language as well. In the ring language, you can talk about definable sets as Boolean combinations and projections of polynomial conditions. But as soon as you add a predicate for the non-zero squares, the set of squares saying a polynomial is a square or is not a square and so on, you again also in the reals have quantifier elimination. In the p-adics, you don't just have the squares, you add a predicate for the n powers for each natural number n. Now, let X in QPN be a definable set. Let it be given. I'm going to define a very important algebra of functions on that set X. So I denote it there as an algebra C of X, and it's a Q algebra of functions from X to the real numbers, generated as a Q algebra by two kinds of generators, which are both natural and simple and easy to define. First generator is of the following form. You send an element, a tuple X lying in capital X, to the p-adic norm of f of X, where f itself is a definable function from X to QP. Definable, and any definable function can be used in this kind of generator. Definable function meaning that the graph is a definable set. And then the second kind of generator is equally simple, from X to the real numbers, where X is sent to order of G of X. So that's the p-adic order, where here G is again any definable function taking non-zero p-adic value, so that the order is finite. This is G. Why is this algebra nice, apart from being easy and easy to define? That's because of a cornerstone result about integration called stability. You can call it, see it as a kind of stability under integration of the class of functions C on any definable set. And that's a theorem going back to Denef, but in a slightly generalized and more generally relaxed form on the conditions with Gordon and Halupchuk, and myself also. So that's the following, and this kind of stability under integration will be come back later in different forms. So consider a function inside this algebra, but now the domain is any definable set times QP to the n, to some power n. And do this again. Then there is automatically, there is a G in the variables just running over the set X, such that G of X equals an integral, whenever that makes sense, which I will specify a bit later, fxy dy. Just go down a bit and then make it a bit bigger again. This is then y running over qp to the n. We integrate with respect to the H measure, normalized as usual, that cp to the n has measure 1. And this equality holds whenever the right-hand side makes sense. So that means when x is such that, for any x satisfying the condition that the function in y is integrable, L1, in the Lebesgue sense for the H measure. It's a kind of an interpolation result or extrapolation for the integrals. So you remain in the same class. That means you bring in manipulations on these functions. You have a function of the class. You can perform integration with respect to some variables, and you stay in the same class. Another operation that I will not talk so much today about, you can also do a change of variables. That means pulling back along a definable bijection, adjusting via the order of the Jacobian, and the pullback will also lie in the same class C of the corresponding definable set. So you have some operations that come in. There is an optional enrichment of this algebra that I want to describe, that one could also add or consider to add as a new generators to form a bigger algebra, a generator of the kind x goes to norm of fx to the power s for s complex variables, say with real part bigger than 0, and generators of the form chi of g of x for each multiplicative character with finite image from qp star to c star with finite image. You could add a generator of that form where again f and g are say definable functions, g being non-zero, taking non-zero values. But this is not such an interesting enrichment of the algebra, because to do Mellin transformation, you don't need just to look at individual chi one after the other. In fact, a Mellin transform can depend on infinitely many chi. So if you add for each chi, you add one kind of generator, you lose a little bit of uniformity. So for Mellin transform, this is not yet interesting enough. Although Iguza, in his very special situation where he looked at twisted local zeta functions, he could get away with finitely many multiplicative characters, because things were enough locally constant for him to get away with finitely many multiplicative characters. I will come back to Mellin transform in a slightly more powerful setting at the end of the talk. But right away, what works more interestingly and more naturally, more easily, is the Fourier transform and things related to the Fourier transform. In this setting of a fixed QP, it's very direct and very efficient to explain. You can enrich the algebra and make a new algebra, Cexp of x. This algebra is now generated by the previous one. So we keep all the previous generators and we add one more kind of generator for functions now complex valued, sending x an element x to psi of f of x, where again f is a definable function, meaning definable graph, that the graph is a definable set, and psi is an additive character with a certain fixed conductor to the complex numbers, so with the plus and here times, and group homomorphism, continuous group homomorphism. And for concreteness, you can choose psi in a specific way if you prefer. For a p-adic number, you can choose it to be 2 pi I with the complex exponential to x prime, where x prime lives in Z with prime inverted and approximates x rather well. So the p-adic norm is at most 1. If you approximate x by a rational number in this ring, this gives a well-defined complex number, and that gives an additive character. All other multiplicative characters are multiples of this one, so you can take this choice or any other choice, or it's not of a big difference right now what you choose exactly. So then there is again the result of stability, which again under slightly less general conditions was given with Lézère and slightly generalized with Gordon and Halukchok. It's the stability for the class Cexp. And now this flexibility in integrability becomes more subtle in the integrability conditions, because oscillatory functions to see when they are L1 can be a delicate question. So this gives in particular also stability of the Cx class of the Fourier transform of an L1 function. So Fourier of an L1 function remains in the class, and it immediately raises a new question. What about Fourier of an L2 function? For Fourier of an L2 function, that's not given by an integral. If you happen to be an L2 function that you live in Cexp, your Fourier transform is not given by an integral. It's a limit of Fourier transforms. It's an L2 limit of Fourier transforms of functions which are both L1 and L2. So it raises the question naturally, what about limits? Can one take L2 limits inside the Cexp class? So this is principle. You want to discover the flexibilities, the operations under which you are stable. And in the same work with Gordon and Halupchuk, we develop several kinds of limits which live inside and which are stable, can be stably taken inside the class of Cexp functions. So the analysis and the stability of under operations bring in natural new questions and new challenges. Let me go to a very big other analogy and very big other challenge. What about the case for F, Q, double parentheses, T? So the Larraur series field over a finite field. You can start again exactly in the same way with definable sets in the language of rings. And close up undertaking zero low C Boolean combinations and projections and finite iterations of combinations of these conditions. That stuff is harmless. It's just a definition. But right away at the first step we did in the fixed p-adic case, it breaks down here. There is no simplification for that kind of definable set. So there is no simplification. The quantifiers and the projections that can come up cannot in general, not yet at least, be simplified. And there is even no conjectural form of how they could be simplified. In the p-adics, it was the power predicates that help you out. Here, there is no even precise conjecture. One of the proofs for the p-adic simplification result, the p-adic quantifier elimination, was first proved by McIntyre using a p-adic argument, but then the Neff gave two new proofs of that p-adic quantifier elimination, one using cells, which is a technique introduced by Paul Cohen for studying decidability of the p-adics algorithmically in that language, and another using a precise form of resolution of singularities closely related to toroidalizations. And this proof, of course, gives a clear hint that at least certainly this proof is not available in positive characteristics. So the question then becomes how to recover some of the results and some of the definitions and stabilities and so on for some of the fields FQT. And then what will it mean? It will actually mean large characteristic. So there is a possibility to recover that. And how can one recover large P positive characteristic from a p-adic case? The answer is work uniformly p-adically in P. So let's now start working and doing some of the necessary changes when we pass to a uniform framework, p-adic in P. And what do I mean here? Ideally, and actually it's the case, it's in all the finite field extensions. So all the finite field extensions and all the primes. So I don't want to fix finite ramification or some degrees or something. This is the goal for the generality to go to, and we do that in two steps. So all K and all primes. First step is to replace QP as the field and taking subsets of QP, replace it by a sort of variables named valued field variables. And this can specialize to K or to QP, so to any valued field actually. We also have a sort for the value group variables, which in our case will typically specialize to the integers. In a framework by Ruszowski and Kazdan, this would specialize to more like a densely ordered group. And then we also have the residue field sort, which in our case usually will always be a finite field. So we will have three variables of three sorts of kinds. We will have many variables running over the valued field, many variables running over the value group, and variables running over the residue field. And we have polynomial conditions can live on these variables. The order of a polynomial can be compared to variables running here, and so on. So we have new sets of Boolean combinations that make sense and are interpretable in all the K and all the p-adic fields that I mentioned. This setup, mutatis mutandis, so with very important but natural adaptations, makes already sense for all extensions of QP, but assuming large P. So now we want to drop the large P, and this setup already also makes sense for all the fields of the form FQT, again, large P. And this large P is unavoidable. We cannot drop because of the problems I mentioned, but this we want to drop. I want to drop it. And that is by generalizing this one step further. Instead of RF, the residue field, we look at residue rings, Rn. Let me denote it by R index order of n, because that's going to be more handy a bit later. And by this, I mean not the residue field, but if I specialize my valued field to K, then this will be the valuation ring of K divided out by the multiple I obtained by the ideal obtained by taking the maximal ideal mk multiplied with the integer n. So n here is a positive integer. And these residue rings, they can be huge if the ramification modulo a prime divisor of n is huge. But they are somehow uniform for large P. This becomes the residue field again, so it falls back to the previous system. So this is to cover also the small primes in a uniform way that treats large P and small p at the same time. So a definable set now is given by conditions, by a formula in a certain language involving the many sorts of variables. And a definable set now can be interpreted inside a finite field, and then we just put inside the p-adic field, we just put an index k, and it becomes a concrete subset, maybe of k to the n of some dimension power n, and the integers to some other power maybe, and maybe also the residue field, which is OK modulo mk, or some of the residue rings to some power as well. Now for the algebra C of x and Cx of x, they can be generalized similarly, where all the pieces that describe the generators, they were actually coming from definable functions. And now definable functions are again given by a description. And if I have a definable function on an abstract set to something, I can put a k underneath it. It becomes a real function again, just to the usual classical number. So I get uniform descriptions of sets and of functions on the sets. And again, everything I said until now, mutatis mutandis, goes through, including the stability under Fourier transform and under integration and L2 Fourier transform and so on. But with this uniform description, there come new questions and new challenges. And also this uniformity has already led to some applications. So I will sketch you some applications and some new recent questions and recent challenges. Yeah, before I do that, let me give you one more aspect of this mutatis mutandis, where I say I take now here residue field, valued field, and value group. But how do you adapt the generators? The generators have to become a bit richer. For example, here I have to allow counting on finite definable subsets of the residue field so that you can count on finite fields. Here I have some generators that do the counting over finite field, could count the squares inside FQ. Here the technique to make it work is to look at either balls, take the volume, and points, they have measure 0. And here on VG, once you're on Z, you just do summation typically of geometric power series or derivatives of geometric power series, like Q to the I minus I times I, and you sum over positive I. So this is how and why it works. And that's the generators now also have a counting new kind of generator that comes from counting over definable sets in the residue field sort. And same for the residue rings. Very classically, the beginning, a question by Borovic and Zafarevic, addressed by Iguza. You can look at numbers, and I normalized them already a little bit by dividing by something, and you just count points modulo p to the m in n variables, such that a given polynomial f of x is congruent to 0 modulo p to the m. This is f is a polynomial, say in x. These numbers allow you to form a Poincaré series, for example. You can do it also for k instead of qp, and then you can form these Poincaré series and call it pk, Poincaré series of the variable t. For example, Iguza showed its rational function in t, but by our uniform understanding of p-adic integrals, we now know a uniform description of this rational form of this Poincaré series. For example, a uniform description of the denominator and the numerator, uniform description of a finite list of candidate poles for this function that work for all these p-adic fields. This was already known by techniques introduced by Deneuve for resolutions of singularities with good reduction modulo p that took care of uniformity aspects for large primes, but with the cell decomposition techniques and so on, slightly more modern insights for the completely uniform C-class, you can also recover all the primes and get a uniform description. And let's look at an important aspect of this Poincaré series, and that is the largest pole. So for each of these rational functions, I can look at the largest pole. And the poles, I will rewrite them. If I have a pole T0, I can rewrite it as p to the power minus some value S0. And then I take the real part of this S0, and this is actually going to be a rational number. For this number, there are only finitely many candidates. They are negative, so they are negative. And I look at the largest one, so closest to 0. That's what I mean by the largest pole. So the negative rational number closest to 0. And actually, this largest pole, let's call it Sk, because it depends on the field that you look at, where k, for each finite field extension of each QP, you can look at that largest pole. Now, let me tell you a little bit that you have for this situation a good descent property, namely Sk is automatically closer to 0, or at least as close to 0 as QP. So if you go to a smaller p-adic field, you have a semi-continuous behavior. You have an automatic inequality. And moreover, since Sk runs over a finite set of possible candidate poles that can ever occur, there is a limit value as K prime, limit value for very large field extension of QP and for P large. In both directions, you take the limit, and this is known to be equal to the log canonical threshold of F. So this limit value stables out because of the descent property. It becomes equal to the log canonical threshold, and by this equality, you win a lot. For example, semi-continuity in families. If you have a family of polynomials, for this risky topology, with some conditions, you have semi-continuity, and you have restriction theorems that if you restrict to a lower dimensional affine space, for example, there is again weak inequality. So semi-continuity, it can only become up to minus sign. It can only move in one direction. So descent gives a limit value, semi-continuity in this case, and restriction theorems. And let us now go to some new situations in which many aspects of descent are yet to be discovered. And yeah, if you want, I can give at some point an example where this can be a strict inequality. But let me now go to the new situation where I will sketch several situations where the descent is highly complicated. For example, for this very same Poincaré series, pk of T, you can look at the largest non-trivial pole. And this is obtained by killing one pole with multiplicity 1. You do the same thing as above, but for the thing where you have killed one pole. So this factor kills the pole of as the pole -1. It is killed with multiplicity 1 by this factor. So if the largest pole happened to be -1 with multiplicity 1, it is killed. So the largest pole will become more negative, could become -2. For this one, it's much harder to see, and it's an open question actually, whether you have any kind of descent. If yes, you would get a kind of limit value, but we don't know if it goes in one. But you can look at the limit value for large P and large finite field extension and take a supremum or some sublim or some inflim. That you can still do. And then there is another question whether you fall back on the minimal exponent. So if you take a limit value and the sublim, do you fall back on the minimal exponent? That's open also, but that would again yield a lot of interesting consequences, like again the semi-continuity and restriction results as recently obtained in this generality by Mustatsa and Poppa. But the minimal exponent is the largest non-trivial zero of the Bernstein polynomial. So here you take the Bernstein polynomial of f, you kill the trivial zero by dividing, you kill the 0 -1. I think that's then you divide by s plus 1. And then you take the largest zero of that one. That's called the minimal exponent. It's known in full generality by Mustatsa and Poppa that it's continuous and restriction. Before that, special cases were known by Malgrange, Lezer, that it's that this one is also semi-continuous and so on. And in fact, in this is closely related to a real and rather a complex situation. The minimal exponent can be seen with D modules and Hodge modules and so on, also by oscillatory integrals and local zeta functions on the complex numbers. as a certain occurring largest non-trivial pole. You have also a descent, which is not so interesting because you have only one subfield from C to R on which you can integrate. You have this kind of inequality coming from the theory of D modules and so on. And Malgrange studied this deeply some decades ago. But it is the deep understanding of the complex case that makes a link between the oscillatory integrals, the complex local zeta functions, and the Bernstein polynomials. And that deep understanding is missing in the p-adic case. In the p-adic case, for this largest non-trivial pole, what is a difficulty? That is that the leading coefficient of that pole, called the residue of the pole, of the largest non-trivial pole, that residue is not positive. It could be of the form you count on a definable set over a finite field, and you subtract the counting on another definable set of the residue field, and that kind of counting is in general could be sometimes positive, sometimes negative, sometimes zero. It can be that on a small field FP, you only see the X part, and this is zero. But on a field extension, this may become have more visible points. So it may, the difference may become zero. And that can jump actually very many times because of, not only because of the difference and seeing more and more points and so on, but also because of quantifiers can explain, can create strange jumps when you go from FP to FP squared to FP cube and so on. So such a difference, which is non-negative, not positive, can create problems because it's not positive and because quantifiers can make it jump around. I will come to other challenges related to descent later, but let me first give some more results and more questions on for the uniform approach. So this is it for descent for the moment. We'll come back to it. But the uniform aspect does not only lead to a certain understanding of the FPT case, it also allows you to transfer some results that are only known in some characteristic to another characteristic. And let me just list a few of these results very briefly. I've listed them before, but since it's a partial overview of applications, let me list briefly again. And Gauss fundamental lemma from the Langlands program and several of its variants, like a Jacquet variant of the fundamental lemma and weighted variants and so on, they all go with some work, can be seen to go about equality of certain integrals in the FQT case. And the ingredients of the integral turn out to be of uniform CX class. They are of CX nature. And of course, over FQT, you have the Algebraic homology, you have geometry that you can use. So in this setting, Ngo was able to prove the fundamental lemma. And by the transfer principle, an equality goes to the p-adic case. So you have the same fundamental lemma in the p-adic case for large P. Just by showing that the ingredients that go into the integrals are of CX class. By independent work by Hales, this also implies the fundamental lemma for small p in the p-adic case. So that's luck, extra work, of course, that you can recover finitely many small primes. This fundamental lemma in work in progress by Forêt, Lezer, and WIS, they want to do more than just having a p-adic and an FQ2 fundamental lemma. They want to really do it at a level of an equality of motivic integrals. And for motivic integrals, the key aspect is that instead of considering a uniform way of counting uniform over the finite field, but with a fixed description, a formula on what you count, motivic integration basically replaces that by taking an isomorphism class of X in some kind of ring of constructed with isomorphism classes, often called the Grothendieck ring of isomorphism classes of definable sets in this generality. So it's a Grothendieck ring of definable sets, potentially even with extra data involving finite field exponential sums. So it's an exponential kind or a Grothendieck ring of varieties with data for some exponential sums or some. So it's not only the counting, can also be finite exponential sums that it codes over of some then some definable function on the residue field level again, and that can also be encoded by a certain class in a certain enriched Grothendieck ring. Another topic is it's not only equality of p-adic integrals that can be transferred. One can also look at the local L1 results by Harishchandra, and he has a lot of local L1 results in the p-adic case. So in the p-adic case, using a lot of deep techniques and analytic techniques, he proves from various objects that they are given by locally L1 functions. And this was a long time open in the positive characteristic case, but then it works also in the FQT case, this local integrability, but this one really has to, for the moment, restrict to large P. And this is work with Gordon and Halukzok from some time ago. So this transfer and to understand integrability properties and what the integrability is a real Lebesgue notion in the p-adic case, and at the motivic level, integrability is a bit more abstract notion, less intrinsic. But these analytic notions and these operations and so on, they are really handy for this kind of result because you can manipulate the thing, you can take Fourier transforms and so on. You stay in the same class and whatever that is used in this ingredient because it's after Fourier transform and so on that things are transferred for in this proof here. Let's now go back to a new challenge for descent. I promised to go back to descent. This Poincaré series that I mentioned, raised by Borovic and Safarovic, has a very natural variant raised by Serre. Serre came up with a variant where instead of the n numbers, you take the n tilde numbers and you normalize in the same way, but now you count on a tube. So you look at the same candidate set, modulo p to the m, but you have your polynomial condition that you make exact p-adically in other variables, and you want that there is a solution. So it's a real solution in the p-adic numbers that is congruent as a tuple to X. So this can be seen as a tube, and you count in the reduction of the tube of the real zero locus. So this is the real zero locus of a polynomial. You can form a Poincaré series for any finite field extension of any p-adic field again, and you can talk again about the largest pole, maybe also the largest non-trivial pole if you want, in the same sense as before. But this was inaccessible by Iguza's method, which used resolution of singularities, because it involves quantifiers. So you have a description involving quantifiers, how to see that this is also rational. Of course, elimination of quantifiers helps you out, but that creates a new list of polynomials that describe your same set without quantifiers. And then you have to resolve you calculate a new integral with new polynomials. So the geometry is a little bit lost. New polynomials come up, so it's hard to control exactly the largest pole, and does it have descent and so on. Also, this can be done uniformly again in K and in QP because there are uniform quantifier elimination procedures in this language that I specified with these residue rings and value group. For this largest pole, you can ask the questions descent, limit value, semi-continuity, restriction, natural questions about this largest pole. And I will come back a bit later to some positive answers to a few number of these questions. Let me first give another list of challenges. You can also look for descent of some properties. And this is all open, what I'm going to say now. So for all the p-adic fields, or you can go even bigger, they compare k prime to k. You have x and you have a function of cx class on a domain X, a definable set, uniformly. Say I know something about fk. For example, fk is L1, or it is locally L1, or maybe you want it to be L2 or something. And then the big question here is, what can you say about fk prime or the other direction fqp? And when can you say something? What nice conditions do you have to impose on f in order to have some descent of L1, L2, and so on? And how can you prove it? We have no idea yet. We have talked with Rami Eisenbrut and Sayek how to find natural conditions and some technique to descend local L1 properties and so on, but it's still a challenge. Here is a problem in the CX class. The two problems arise. You have no natural notion of positivity because it's oscillatory. So you have the complex numbers, exponential sums go in all complex directions, and you have quantifiers in the descriptions. So going to a larger field can make you jump around if you take sums and counting. Larger fields doesn't say that things grow compared to the smaller fields. Yeah, let me now announce very briefly the first positive result of a new result about descent. That's joint work with my PhD student Stout, and that is for the Serre variant. The weak inequality when you go from the largest pole to SQP, this is what works. And was it this inequality? Yeah, if you go to a larger field, then you get closer to 0. So the largest pole becomes closer to 0, k bigger than QP. What's the ingredient? We need a double notion of positivity. Double notion of positivity. There was already an existing notion of a variant of Cx which has a formal kind of positivity, and that was motivically developed with Lazare by myself and adapted p-adically, uniformly p-adically with Itai Glaser and Jotam Hendel. And this is then a uniform class of formally positive functions. The stability of under integration in all these cases becomes a little bit more tricky. So stability you have to assume better integrability conditions. So let me call it then stability, assuming a good L1, better, stronger L1 uniformly for all the parameters, then you get stability. So that's a variant of the stability. But as I showed you, stability and positivity is not enough to have descent. The double positivity builds in an extra aspect, which we now denote by CE plus for the new aspect of positivity, and that is control on the quantifiers. Control on the quantifiers that is such that counting can only grow if you go to a grower field, to a larger field. And there is an easy trick. If you have an existential formula, meaning you have first some existential quantifiers and then a formula. So here's y1 to up 1, and then a formula without quantifiers. And if this is my formula describing my set X, if I then count on X in a small field, it can only grow when I go to a larger field. So p square and so on. It can only grow because, of course, for quantifier free, this is not so difficult to see, but with the quantifiers, if you have a witness, these are witnesses. If the witnesses already exist in small fields, they will also exist in large fields. So you have more and more solutions. So the existential formulas are kind of the most general kind of formulas that always have this behavior that they grow in larger structures. There is also always an inclusion of sets. So this set is automatically included as that set if if you look at FP as included in FP square. So this double positivity gets us around for the largest pole of this Serre variant, but not at all for the largest non-trivial pole, because there it's again a difference. Could be counting on X minus counting on Y. So because of this descent, we have a limit value as K for K very big and P large. But this limit value, we don't know at all whether it's nice. Is it semi-continuous? Does it have some kind of restriction properties? That's a question. Why do we need these existential formulas? Why can't we work with quantifier-free formulas and count on these? Because they also, of course, only grow. That's because the Serre variant is starting with existential quantifiers. So it already has existential quantifiers. So we just stay in that formalism. It's an existential description of the Serre variant that we push down to an existential description on the residue field level. Yeah. For the semi-continuity and the restriction, it's very difficult because in the p-adic integral, if you manipulate p-adic integrals, you have a combination of p-adic topology. Yeah, you have, if you want semi-continuity, that means you have a Zariski stratification, but you can approach the boundary of a Zariski stratum in the p-adic topology. So it's a mixture of p-adic and Zariski topologies that are difficult to control by just looking at integrals. So semi-continuity is unclear how to get it. I'm jumping around between descent challenges and uniform challenges and uniform results. Let me jump now back to one more uniform results that I recently obtained with Eisenbud, and which partially also is still a challenge that I will mention. On QPN or on K to the N, there is a natural notion of CX class distributions. And that's just if you have even uniformly, you can talk about it uniformly. And that's, you have a distribution, you take its wavelet transform where the mother wavelet is just the characteristic function of a ball inside QP to the n. If that wavelet transform is of CX class, then you call your distribution of CX class, meaning that you evaluate your distribution in the family of all the balls. That's a family of Schwarzschild functions. When you move in that family of Schwarzschild functions, you get the real complex value output each time. If that's a CX class dependence, you call your distribution of that CX class also. And we showed that these are automatically wavefront holonomic. And this wavefront holonomic is a proxy notion introduced by Drinfeld and Eisenbut recently that wants to introduce new analogous notion in the p-adic world for powerful objects in the real and complex world. It's an avatar of holonomic in the real deep meaning in the complex world. Here it's more, a little bit more less powerful and more ad hoc notion. But all these distributions are of that holonomic kind. And moreover, the CX class distributions are stable under taking Fourier transform. And this was an explicit open question in this work by Drinfeld and Eisenbut. Can you find a framework that is stable under Fourier transform and that preserves WF holonomicity? Because the notion itself is not stable under Fourier transform of distributions. And let me now come to the open aspects. That's actually the real case. So this is the other way around. We have a p-adic results, and in the real case, it's an open question. In the real case on Rn, you can also talk about CX class distributions by a similar way. You take the mother wavelet to be the Gaussian. You let that Gaussian become a wavelet transform by evaluating your distribution in the family of all the Gauss test functions. And if that dependence is of CX class, so there exists a notion of CX functions also on the reals. If that's of CX class, you call your distribution of CX class. And we want to see whether CX class distribution are actually naturally analytically holonomic. I will not go into details, but there is a very natural notion of algebraic holonomicity. There is a more technical, more involved notion of analytic holonomicity. And this is not a stable notion under Fourier transform, the analytic holonomicity. But it's work in progress with Eisenbut to try to show this. And this again would find a framework of distributions which is stable under Fourier transform and which are all analytically holonomic. This depends still on a hanging result about integrability issues of CX class functions that we know yet in low dimension, but not yet in full dimension. So there is some L1 issue still hanging. Yeah, I have like 1 minute. Is that okay? Because I started 1 minute late. I will take 1 more minute. And now I made a lot of promises in this talk, but the very first promise I made, everybody forgot probably, is to come back to Mellin transformation in a slightly more richer way than with just for each multi-clear character adding a new generator. So this is work in progress with postdoc Nguyen and Lazare. And what does it do on a uniform p-adic level? Remember, we had these sorts, the order of n, the residue rings, the valued fields, and the value group. And we have a natural language talking about the 3 kinds of variables and so on. Now we enrich first with a very, very simple basic step. Here we add constant symbols, L1, L2, L3. And constant symbols are the tamest object of model theory. They behave informally as they can be used like variables, except they can never occur in a quantifier. A variable can occur in a quantifier, a constant symbol can occur like a variable, but never in a quantifier. So this is nothing, just add constant symbols. This is nothing, even we do a trick, we specify nothing about the constant symbols. So in a way, they are free constant symbols that can at the end be chosen, be given any value. So in that respect, they are like a variable. At the end, if you have a description of your functions and sets, you can let lambda1 move over the whole value group, and it will be a function then in that constant symbol, because we specify nothing about it, no specification. So it's a hybrid situation between a constant and a variable. We only require them to be positive, and now we use them to introduce new sorts, and that's a bit of a little bit tricky to use constant symbols to axiomatize sorts. And these are new residue rings where we have the order of n plus lambda I for each natural number n, and each of the constant symbols we have a new residue ring. And this picks the conductor of the multiplicative character. So we don't have to fix character chi, which lives on some. Character chi always lives on some of these. No, we put them in a family by having a sort growing, or at the end you can choose, let it vary over all conductors. On the value group, of course, the value group is Z. The Mellin transform just lives on the circle, the unit circle, so that becomes the rationality result. It's still visible if you sum t to the I for positive I. That's typical a Mellin transform on Z. It becomes a function on the unit circle, which is a rational function. It's like 1 over 1 minus t that lives on the circle. So the Mellin transform there is not a real challenge. And then I've used all my time. So I thank you all for your attention. I hope I had a good connection, and that's it. Thank you.
Thank you very much. Questions, please.
So please raise any questions.
Hello.
Yep.
Hi. It's a bit vague, but is there any hope of getting those rationality results for FPT by somehow approximating FPT by highly ramified p-adic fields? I mean, this must have been.
That's, one can hope, of course, but I don't see a plausible strategy yet. I cannot see it, because in this ring R or n, even R, the order of the prime P, if you go, as you say, you ramify your p-adic fields, that means that more and more of the complexity and the difficulties will be inside that ring. But this ring, remember what it is, it's OK modulo P times the maximal ideal. This is the zero ring in FPT, so it collapses. Is that right? No, sorry. In FPT, it's the zero ideal. The ideal collapses to the zero ideal. So that means that instead of putting your complex things in a finite ring, you put complex information in itself for, so the valuation ring of FQT. And that cannot be of any help. To put your own in yourself does not help you here. Mm-hmm. So this is, I don't see any plausible strategy, but one can hope. Yes.
Okay. Thank you.
Can I ask a
sure.
vague question? Hi, Raf.
Sure.
Yeah. Thanks for the nice talk.
Thanks.
It's a vague question. So these counting results that you mentioned, so I mean, I know kind of examples how it works with the cell decomposition type technology. are there results which are proved using not a normalization? I mean, because it seems that when you have a not a normalized set, in some sense, you know, counting points in the set is the same as counting in the base, you know, times the size of the fiber. So it seems plausible. I was wondering if there is something done like this.
You mean something done differently?
I mean, are there versions of these proofs where instead of using the cell decomposition type technology, you use not a normalization type things, which are a little bit different and maybe easier to work in the positive characteristic case?
Yeah, not that I know of, and as I know Noether normalization, it gives natural upper bounds, but maybe not such a precise exact counting. And here we want to keep equality after integration. We still want to say it's exactly this value and not just, but that's not a deep answer, of course. I think cell decomposition can be seen a little bit like covering, as you say, because you have your base set and then you have finitely many graphs on top of it. So you count the number of graphs, that becomes a factor of the measure of the base. So that's kind of the flavor that you mentioned.
Yeah, I mean, it's just that when you have not a normalization, you have a base and you know that you have the same number of fibers everywhere. So yeah, presumably you don't need to really choose each branch separately. You can just say it's the base times n, where n is the
exact number of fiber. Is this also on the QP level or is this on the CP level?
Yeah, okay, this is a deeper question than I maybe.
So that depends a little bit, because here on each p-adic field we want to do the precise exact calculation.
Yeah, I see it. Okay, thank you.
Questions, suggestions?
If there are no further questions, let us thank the speaker again. Our next talk is in 2 weeks. Alexander Yomdin will be speaking on a joint work with David Kashdan, probably, on tempered representations. So thank you again, Raf, and see you all in 2 weeks.
Thanks.
Maybe I can ask a quick, another informal question.
Sure.
Yeah. So you mentioned at some point this motivic version of these results. So I was wondering, is there something done like that in the real situation? I mean, I suppose you could define, you know, bijections that preserve volume.
Yeah. Yeah, I think there are some attempts in that direction, but it's not so intrinsic how to define it. So there are some choices made, I think, by Georges Comte, among others, who developed that in some extent. But then you have to make choices what to present motivically and how to present it motivically. You want to make natural choices, of course, but it's always a little bit of a choice, I would say. Georges Comte looks at isomorphism classes of real semi-algebraic sets, which can also have a complex interpretation, and so he links these informations together. And then you can generalize some of the real classical results into that setting and so on. Yeah, but I don't know if it's really applicable to new open questions, not yet maybe, or yeah.
Yeah, it's just that I've never heard of anything like that.
Yeah, I think Georges Comte, in collaboration with some people, you can ask him, or we can ask him, or no.
Yeah, well, it's just curious. Not that I have anything specific in mind. Whenever there's something p-adic, then try to do it also.
Yes, but the CX class has been developed in the reals.
Yeah, this you mentioned.
Yeah. Okay, this was the first time this kind of a hybrid talk, with actually a hybrid role of how do you say that, the person who announces the talk and so on, and
So what is your setup exactly? You're writing on the iPad.
I can show it. I'm writing on some tablet. It's being projected, and I'm speaking loudly for an audience. So I had to figure out a bit about the setup, how to try to do it, but it didn't break down or so. So it was.
No, it worked. I thought it was fine.
Yeah.
You were clearly audible. So.
Yeah. So now here is a coffee break.
Yeah, we should order on the internet coffee for the speaker. That's the next thing our seminar should do.
Yeah, and I want to open the windows.
Okay.
So let me say goodbye, and let's Zoom and discuss later again, because now it's here like a coffee break.